Total area of Iran is 1.65 million square kilometer. Total population about 78 million. Annual precipitation average 250 millimeter. Range from 50 millimeter to more than 2,300 millimeter. Diversity. No rainfall in late spring, summer, and early fall, except in Caspian Sea. Temperature minus 30 to more than 55 degrees centigrade. It's unbelievable. That's true. Elevation, sea level to more than 5,000 meters above the sea level. Climate arid, semi-arid, cool, temperate. Actually, Iran is a country of diversity in all aspects. Let's have a trip to Iran, free of any cost. So, this is the Caspian Sea, rainy forest, more than 2,000 millimeter rainfall, high mountain, full of snow, high mountain during the summer, no rainfall, and again high mountain and mountain forest in cool area. The same climate and desert. Nothing is in it. And sand dune in arid area, very hot, and salt pan in Kavir in desert. And salt diapirs, more than 120 diapirs in south of Iran, deteriorate the good quality of water. I invite you to come to Iran and see this unique diapir. Another picture, and the Persian Gulf. You can swim during the summer. And the biggest salt cave in the world, discovered by a group of Czechs and Iranians from Shiraz University in Qeshm Island. Let's go to water resources. Average rainfall is 412 billion cubic meter, but 295 billion cubic meter of this water evaporate each year. What remains? 130 billion cubic meter total renewable water that we may use it. And per capita water usage is 2,000 cubic meter per year, and it's predicted to reach 700 cubic meters soon. Agriculture. Total area is 165 million hectare. Total cultivated area is only 12%. That only 7% of total cultivated area is irrigated farming. The rest is dry farming. Ancient water management. The arid to semi-arid and limited surface water encouraged ancient Iranians to develop technologies as early as 40,000 BC as qanats, water wheel, abambar, and dams. This is a typical abambar. Thousands of them in semi-arid area. The source of water is runoff from precipitation. Right now, no use. You can see the abambar everywhere, but we don't use it anymore. And this is a very sophisticated abambar in Yas city. It's a very beautiful city. It has 5 wind towers. And this is the entrance to the abambar or water storage for the municipal city of Yazd. And this is a water wheel. The well is here. And the cow was used to raise the water from the well. It's easy to do the job down a slope. And this is the water storage, and the water is discharged into in this canal. We don't have it anymore. Qanat. Qanat invented by Iranian more than 2,500 years ago. Qanat drain groundwater of aquifer and transfer it to the surface by gravity. Qanat lengths vary between 1 kilometer to 70 kilometers. This is a qanat. This is the access shaft. This is the channel. The slope is less than the ground slope, so we can transfer the water of the aquifer by the gravity to the surface. So this part is very important because this part is located below the ground table, water table. It collects the water of adjacent aquifer. Sometimes this part is more than 40 kilometers. Why? Because it collects the water from the aqueduct. Perhaps in a very fine material, it can get only 1 liter per 1 kilometer, but when it is 40 kilometers, it gets 40 liters per second. That it is sufficient water in a desert area. But with the well, you cannot get such a water in acute or in very fine material. This is the main advantage of qanat. This is the qanat shaft access. You can see a garden around here that's irrigated by the qanat. And this is another picture, shows three qanat in a desert. And this is the qanat channel without lining. And this one with lining. Qanat characteristics. Qanat is the most environmental and sustainable method of groundwater withdrawal. Negligible evaporation. No over-exploitation at all. Draining sufficient water from aqueduct through a long distance, but negligible discharge by pumping well, in comparing to the pumping well. No electricity needed to raise the water. And also it is a cooling system. The hot air flow into the access shaft. It passes on the qanat water. It cools, go to the houses, cool the houses, and flow outside through wind tower. A circulation of, it's fantastic. This is the wind tower in Yas City. This is a desert. No water, no vegetation, no shadow, nothing. But in the middle of the desert, you find a garden. Actually, it's not a garden. It's heaven. 100, 200 kilometers, no shade, no water, nothing. Suddenly, you enter a garden. Beautiful. You have another feeling after 100 and 200 driving just in hot weather. This is irrigated by qanat. Qanat provided 75% of the water used in Iran prior to 1950 and irrigated about half of the land under cultivation. But now, less than 10%. Why were replaced qanats? No environmental aspect, but economic aspects. Significantly shorter time for construction and maintenance of wells. High initial and maintenance cost of qanat. Problems of budget collection from tens of qanat stockholders. Social and economic changes. Present water management. The present system of water resources management in Iran has changed under certain social and economic conditions such as population growth, urbanization, fundamental changes in economic system, and modernization. Food security and sustainable agricultural production were one of the main policies of the country. New advances since 50 years ago, such as significant development of agricultural area, construction of extensive dams and recharge basins, construction of 600,000 exploiting wells. Just in 50 years, 600,000 wells. New irrigation system, border, sprinkler, drip irrigation, lining canal, and etc., and etc. This is the dam under operation, about 600, under construction, 140, and under study, about more than 500. Impact of present water management. The food security policy and the need to provide enough food for 70 million people. The population increased about 6 times in 50 years. Resulted in negative water balance in 250 major aquifers. Of the total 600 major and minor aquifers. When I'm talking about 270 major aquifer, negative balance, perhaps 80% of the total water, groundwater, is main aquifer. Sometimes it's 10 times more than the minor aquifer. What's the reason? Hydrological or hydrogeological, and second, economical, cultural, and social. Hydrogeological reason: minimum hydraulic storage, hidden crisis period, low velocity of groundwater flow. Minimum hydraulic seepage: a significant volume of water in excess of the average recharge water or safe yield is stored in an aquifer to provide enough pressure head to push the water toward the discharge zones, such as spring, rivers, and adjacent aquifer. MHS, minimum hydraulic storage, may be fossil or renewable water, may be dynamic or static, but it's very important. It can be used only once. Only once. And it's not part of a conventional water balance. We don't calculate it in the water balance at all. We calculate the different storage, not the total storage. This is a natural system without well. This is the safe yield, and this is the minimum hydraulic system. So, another case, this is safe yield, and this is minimum hydraulic system to push the water toward the recharge. The velocity is too low here. So I calculated the depletion time of MHS in several aquifers. It is more than 50 years in most of the aquifer. What is the hidden water crisis? As a result of long depletion time, more than 50 years, water crisis was not observed until 10 years after the beginning of our drafting. As the water table dropped, the wells were further deepened to withdraw the MHS below the drop water table. This period of over-exploitation with no obvious sign is named hidden water crisis period in this study. So the people were glad. Everybody was happy. We have new cultivation. We have new land. But actually, it was from the MHS, just for a short period. This is hidden crisis because I cannot find the... Okay. Because this part actually, it was here. This part is a part of MHS. Actually, our drafting use MHS. This is hidden crisis because we use MHS as a part of our drafting. And this is the obvious crisis. No more MHS left. So it starts to decrease the discharge of the downstream spring and canal. This is, again, hidden crisis in this kind of aquifer. and again, obvious crisis. The crisis was predicted by specialists in Iran during the hidden period, but they didn't publicize it to officials and farmers. It was only on the report, scientific report. The main reason is it's not a part of our job. So, impact of groundwater overexploitation, significant discharge reduction of downstream spring, canals, wells, and seepage to adjacent rivers, or dried downstream spring and canals. Thousands of canals dried off. Intensification of water scarcity in drought years, because we use the MHS in dry years. It was a very good storage for dry years. So we intensified the dry years. Increase of energy costs forever due to water table drop. I calculated, it's unbelievable. It's huge amount. I am not talking about all of it. Social, economic, and cultural reason of our exploitation. Groundwater was free, with no measurement devices. As a consequence, farmers withdraw water more than the permissible discharge. And sometimes, and most of the time, most of water requirement. They believe the more water, more production. The hidden water crisis was not publicized by the mass media and scientists. Sympathy of society is very important. Sympathy of society for low-income farmers, preventing law enforcement to plug the illegal wells or regulating well discharge. It's very important. Drip irrigation intensified the water crisis in aquifer. You cannot believe it. Drip irrigation? Yes, drip irrigation intensified the water crisis in aquifers with a negative water balance because the safe return flow was used to cultivate new lands. Because we used the return flow in the subsequent wells, it was not lost. But when we had a drip irrigation, we extend the farm, no more return flow. So actually we intensified the water crisis by drip irrigation. The traditional organized irrigation system was abandoned. We had the law. Most of the people obey one person in the past. But right now, nobody obey the other person. Just everybody wants anything he wants. This is civilization. Despite modern agricultural knowledge and technology and adequate investment, the average irrigation efficiency is still less than 33%, and the dry grain yield is 800 grams per 1 cubic meter of applied water. This is due to social, cultural, and educational constraints. 70% of farmers have land smaller than 5 hectares and within several separated locations, one here, 1 hectare here, 1 hectare here. But don't agree to trace for one larger farm. This is a very important problem in Iran. The all-inclusive water resources program of the basin were not implemented due to pressure from the locals. You have studied, you have very good report, but the specialists are not the person that decide about it. Just political forces have the power to change all of the studies. Remediation methods. Raise the water table to the level it had before withdrawing the MHS. This may take several decades. First, integrating research to encourage farmers to further cooperation for optimum groundwater management. Actually, I am disappointed with all of my researchers. I have decided to go to this different city and talk to the people, and I did it. And I was successful. I talked for the religious leader, for governor, and also for the farmers about the crisis, and it was useful. You know, we need research. I'm a hydrogeologist, but I need all of the other branches to do something about this problem. Just help the farmer to change their attitude. Second, installing intelligent meters and fairly distributing the limited water among all the wells, especially during the drought years. Prevention of flow of salty upper brine into adjacent aquifer. Development of drip irrigation without extending cultivated area. We don't have any law about that. Everybody thinks that drip irrigation solves all the problem, all the crisis. But we don't have any law to prevent the people from extending their farm. Improving irrigation efficiency without extending the cultivated area in basin with negative balance. Increasing dry grain yield per unit volume applied water. Providing agricultural water from other sources, increasing water prices, and so on. You know that. Let's go to the conclusion. I want to conclude as a politician and not as a scientist. در ایران بحران آب وجود ندارد. There is no water crisis in Iran. How do you say this sentence in Serbia? Okay. There is no water crisis in Iran. I rejected all of my lecture by this conclusion. We don't have any crisis in Iran. How do I dare say there is a crisis when the average dry grain yield is only 800 grams per 1 cubic meter of applied water, when the world average is 1,200 grams per 1 cubic meter of applied water? If we get to this point, if we have 1,200 grams per 1 cubic of meter, we don't have to import rice, we don't have to import corn, but just we put too much pressure on water resources. Everybody wants to construct dams, to construct richer basin, to build more and to construct more and more well, to deepen the well. Nobody think about this problem because in Iran we have knowledge, the technology, and capital to achieve an efficient modern agricultural system. But our main issue is to overcome the social constraint. There are plans and attempts to overcome this challenge, but they will take time. Thank you very much.